In this project, we address a major financial security challenge, detecting fraudulent transactions hidden within millions of legitimate transfers. To begin, we collect a high-volume, real-world financial dataset from Kaggle. This dataset is already labeled, allowing us to clearly distinguish between genuine and fraudulent transactions and use it to train a supervised machine learning model effectively. First, we import the required Python libraries, mainly pandas for data handling and NumPy for numerical operations, and then load the dataset into our environment. We carefully explore the dataset using functions like df.info to understand the data types and check for missing values, and df.de scribe to analyze statistical measures such as mean, standard deviation, and data distribution. This initial exploration helps us understand the quality of the data and prepares it for further pre-processing and modeling. Next, we perform exploratory data analysis, which is essential for understanding the dataset more deeply. Using visualization libraries like Seaborn and Matplotlib, we create plots to explore transaction behavior. We analyze the frequency of different transaction types and examine the maximum and minimum transaction amounts to detect unusual patterns. These visualizations help us identify trends, outliers, and characteristics that are commonly linked to fraudulent activities, guiding us toward better feature selection and model performance. To gain deeper insights, we generate scatter plots that compare account balances before and after each transaction. These plots help us visually identify unusual balance changes that may indicate fraudulent behavior. Additionally, we create a correlation heat map to understand how different features relate to one another. This heat map clearly highlights which variables, such as transaction amount and balance differences, have a stronger relationship with fraud, helping us focus on the most important features. Before training our machine learning model, proper data pre-processing is a critical step to ensure accurate and reliable results. We begin by splitting the dataset into training and testing sets, which allows us to evaluate the model's performance on data it has never seen before. This step is important because it helps us measure how well the model can generalize, rather than simply memorizing the training data. By doing this, we reduce the risk of overfitting and improve the model's real-world applicability. Next, we separate the input features from the target variable. In our project, the target column is fraud, which clearly labels each transaction as either fraudulent or legitimate. This separation ensures that the model focuses only on the relevant features when learning patterns associated with fraud. Finally, this structured and systematic pre-processing approach helps maintain data integrity and consistency, creating a strong and reliable foundation for effective model training and evaluation. Machine learning models perform better when numerical features are on a similar scale, because large variations in values can affect the learning process. To handle this, we apply the min-max scaler, which normalizes all numerical features into a range between 0 and 1. This prevents features such as transaction amount or balance changes from dominating the model and allows it to learn patterns more evenly. In addition to numerical features, the dataset also contains categorical attributes. For example, transaction types like payment, transfer, and cash out are represented as text. Since machine learning algorithms cannot directly process text data, we use an ordinal encoder to convert these categories into numerical values. This step ensures consistency across all transactions and makes the data fully suitable for model training. After pre-processing, we move on to building the model. We import the Logistic Regression algorithm from the scikit-learn library and train it using the prepared training dataset. Logistic regression is well suited for fraud detection because it is a binary classification problem. Once the model is trained, we evaluate its performance on the test dataset. The model achieves an accuracy of over 99%, indicating a strong ability to distinguish between fraudulent and legitimate transactions. Once the model is trained, we use it to predict outcomes on our training, validation, and test datasets to evaluate its performance. We calculate accuracy scores, which tell us the percentage of correct predictions, and generate a confusion matrix to analyze how many transactions were correctly or incorrectly classified as fraudulent or legitimate. To demonstrate the model's real-world use, we create a new sample transaction with details such as transaction type, amount, and account balances before and after the transaction. This data needs to be pre-processed, just like our training data. First, any missing categorical values are filled with a placeholder. Then, categorical features are transformed using the same encoder applied during training. Similarly, numerical features are normalized using the scaler. After combining these processed features, we feed the new transaction into our trained model for prediction. The model outputs whether this transaction is fraudulent or not. If the result is 0, it indicates no fraud. If 1, fraud is detected. This shows how our system can flag suspicious activity in real time. Thank you for watching this tutorial. If you found it helpful, please like, share, and subscribe to support the channel. Stay tuned for more data science projects and tutorials.